to speak today. It's a pleasure. And thank you all for coming. So I wanted to talk today about sort of the following problem. So the goal is to compute the topology of the space, or I'll just say the topology of the group gamma gamma is going to be some congruence arithmetic subgroup of G of Q. So a perfectly good example would be the set of 4x4 matrices of determinant 1 that are congruent to 1 modulo 17. So gamma acts on its associated symmetric space, which is contractible. And by the topology of gamma, I really mean it's exactly the same thing as the topology of this locally symmetric space, gamma mod x. So the reason that I consider this an important thing to study is because the space, so gamma mod x is acted on by a ring of Hecke operators. And if you look at the action of, it induces an action on, for example, the integral cohomology of this space, and the it's a commutative ring, and the simultaneous the systems of simultaneous Hecke eigenvalues carry deep arithmetic significance. In particular, to study the action of the Hecke algebra on torsion, I don't really know a simpler way than to somehow fully compute a homotopy type. Some sort of finite combinatorial data that would give rise to a chain complex whose cohomology is the same as the cohomology of this space. So that's the goal. There's a large literature at this point of sort of various ways of trying to probe the action of Hecke operators on the cohomology of gamma. It would be impossible to give a complete list of names, but this is a list of some of the names and some of the some methods which have proven fruitful. So I want to talk today about joint work with Aurel Page, where we do something somewhat different than these other methods. We actually compute a sort of a full homotopy type for the group gamma, and we're able to control the sort of the complexity of a certain finite simplicial complex that has the same homotopy type as gamma, and we're able to in principle to compute the actions of Hecke operators on this complex, and we can bound the amount of time it takes for this computation to terminate on a computer. So I spoke about this result at the at the IAS workshop in the IAS workshop in November. Thanks. But I want to, so at that point, so in November, so I spoke about how to build a grid of points on the space gamma mod x. And today, so the basic idea is to sort of, once you have found such a grid of points, the idea is to just look at the open covering given by balls of some radius centered at those points, and to compute the nerve of that covering. And it's an old result in topology that that nerve has the same homotopy type as the space which is being covered. So in November, I spoke about how to build this set of points F. And today, I want to focus on how to actually compute the higher skeleton of the nerve. Or in other words, in November, I talked about how to determine whether two balls in this collection intersect with each other. But now I want to discuss how to determine sort of when three of the balls have a common intersection point, or four of the balls, and so on, and some of the limitations of that. Okay, so I'm going to keep returning in this talk to this one fairly simple example. It's an example of an arithmetic 3-manifold. So we start with a quaternion algebra over that imaginary quadratic field, q adjoin the square root of -2. Take a maximal order in it, and we produce a certain an action of the units of the maximal order. So it acts by conjugation on the trace zero elements of the quaternion algebra, and it preserves a quadratic form on the trace zero elements, namely the reduced norm form. And so you get a certain, a certain arithmetic subgroup of the orthogonal group of that quadratic form that preserves the lattice. And we take a certain principal congruence subgroup, so the set of matrices that are congruent to 1 modulo a certain prime ideal. The subscript on the prime denotes, so the prime 2 is ramified, and the prime 3 splits as a product of 2 primes. So the 2 primes above 3 are, I call them P3 and P3 prime. So we take a sort of the principal congruent subgroup that I've written down there. So I want to tell you what happens when you try to compute. So once you've built a covering of the associated hyperbolic 3-manifold, sort of what comes next? How you would compute the nerve of that covering. Okay, so when I write, so check. So we'll have a certain finite subset of this compact arithmetic 3-manifold that you just take as a black box that it's there, and check R of this thing is the simplicial complex, the check complex for the open cover given by balls of radius r/2 centered at points x where X is in your finite subset. Okay? So for that radius, 0.65, it so happens that these balls are all convex, and they form a good cover of the three-manifold M. And here's some information about how hard it was to compute this check complex. So it took more than 1,000 seconds to compute a cover in the first place, and then to determine whether pairs of balls intersected, it only took about 300 seconds. We started so I wanted to produce an example for this talk, so I decided this afternoon to start running a computation to compute the two skeleton of the nerve, or in other words, when triples of these balls have a common intersection point. And I started running it earlier this afternoon, and it's still not finished, or it's probably very close to finished now. Aurel is running a computation in Bordeaux as we speak, but it's nighttime in Bordeaux, so I'll probably find the result of this computation tomorrow morning. And so I list at the bottom sort of how many simplices there are in each degree, simplices in this check complex. So there are 176 points in the covering, a little more than 3,000 instances where pairs of balls intersect with each other. And then I don't know yet how many two simplices there are in the covering. It's gonna be on the order of something like 6 to 8,000, something like that. But I don't have the complete information yet. Okay. So the check complex evidently is somewhat hard to compute, but I want to describe. I want to spend a while describing, at least in principle, how you can actually how you might reduce the computation of the check complex to a tractable problem. Okay, it's kind of a subtle thing, even in the Euclidean plane. It takes some thought to. You can certainly have situations where you can have three balls in the Euclidean plane that are mutually tangent. Maybe they're like a little bit closer to each other. So they all have pairwise intersection points, but they don't have a common intersection point. So could you think of an algorithm to decide whether three balls in R2 have a common intersection point? I think even that takes some thought. So yeah. When do balls have a common intersection? And in my opinion, it takes thought even in R2. Okay, so before I describe the algorithm to how in principle you can compute the check complex of a covering of a space of this type, I want to remind you of, I'll do like a very fast review of how we actually build a covering of our manifold gamma mod x in the first place, if for no other reason than to remind you of what the input into our algorithm for computing the higher skeleton of the nerve is going to look like. Okay, so so I guess before I do that, I have some other things I wanted to tell you. Oh, okay. So using what we, sort of the information we have so far, using the sort of the partial information that we've computed so far using the check complex, it's still possible to say something interesting. We can still compute a presentation of the group gamma. We can compute its abelianization. And I also wanted to say that in case you don't trust our algorithm, that there's at least some kind of external consistency. We compared it to like other software that you can use to compute with hyperbolic 3 manifolds, and sure enough, for this particular example, the first homology group it agrees with those things as well. Of course, at some point, we're going to venture into the realm of examples where computations are not yet known, but for now, there's this external consistency check. And as I say here, it's sort of the computation starts to get difficult. So now let's do our lightning fast review of how you build coverings of locally symmetric spaces in the first place. So I like to call this algorithm an expanding ball algorithm, because you sort of start from a point, and then you build larger and larger subsets of your manifold by expanding out in a ball shape. So I'll just click through this very quickly. You start with a well-spaced set of blue points, and you add some more points. I didn't want the picture to be too cluttered, but there would be a constellation of points all around the blue points in reality. And every time you sort of go one by one through the yellow points, and every time you have a yellow point which is far from all of the existing blue points, you add it to your set. Okay, so I'll click through very quickly so you see what that looks like. And if you're close to a point which is already blue, then you just forget about your yellow point forever. So if you see this in action, you see some points are disappearing, some are being colored blue. So that point that I colored red, that's very close to an existing blue point, so we discard it. It's somehow redundant. It doesn't really help you cover that much more of the manifold. And in this way, you've produced sort of an extra, this does, okay. So you see you have this extra shell on the boundary. You've pushed the frontier of the set of blue points farther out. You've covered more of your manifold. And if I had made the picture more cluttered and there had been yellow points all around, you would have seen an outer shell sort of all the way around the inner collection of blue points. Okay, so here's a larger scale picture of what this expansion looks like. Okay, if you sort of go through that whole process, like one iteration and then again and again and again, you get something that looks like this. The circle isn't actually shrinking. The picture viewer is just scaling things so that all of the dots fit properly on the page. So this is always the blue circle is always a circle of radius 5. So I'm showing that eventually you do cover this Euclidean circle of radius 5. This is just an application of this expanding ball algorithm in the Euclidean plane. Okay? And then I think 10 iterations later, something like that happens. So the key point here is that so to know whether to keep expanding, or in other words, so for one of those yellow points in those pictures some slides ago, to know whether to turn them blue or to make them disappear, you have to know whether they're close to one of the blue points or far away from all of them. Now, in the Euclidean plane, it's not that hard to compute distances. It would be more subtle to compute distances if you took the quotient of the Euclidean plane by a lattice. Okay, and likewise, if you have a symmetric space, it's not that hard to compute distances in a symmetric space, but in a quotient space like gamma mod x, it's a lot more subtle to compute distances. So the key point is, so you need to compute Riemannian distances in gamma mod x, quotient distances. Distance in x from x to gamma y. So, I mean, so sort of the algorithm, this expanding ball algorithm aside, say that someone gives you a collection of points that they claim covers this manifold gamma mod x. And maybe you believe that that set of points covers gamma mod x, but you want to determine the one nerve of the skeleton of the check complex that is determined by that set of points. I mean, to determine whether two points are adjacent in the check complex, whether they share a common edge, it just boils down to a question of whether those 2 points are close in the quotient. Okay, so you need to be able to compute distances in the quotient, or to determine whether 2 balls intersect. It turns out you only need to compute sort of the minimum of r and the distance in the quotient in order to determine whether 2 balls of radius r intersect each other. Okay. Okay. So one of the key things that this expanding ball algorithm does in the context of locally symmetric spaces, so one of the things our algorithm does is given 2 points, x, y, and x. So say we want to determine if they have distance less than or equal to 1 away from each other in the quotient. So what we do is we compute. So we compute a finite list. So let me call it L, gamma 1 up to gamma n of elements, for which if an element of gamma moves x close to y, it has to be from among the elements of this list. So if the distance between the gamma translate of x and y is less than or equal to 1, this implies that gamma equals gamma 1 or gamma 2, one of the things in this list. Okay, so this is the data that I want to start with when I compute sort of whether, say, 3 balls have a common intersection point in the quotient. Okay, this is the sort of data that I want. Okay. Right. So let me explain how to use this information to compute whether balls have a common intersection point. So the first step is to reduce this to a question about whether balls intersect in the symmetric space itself. Okay, so I should say, by the way, that if this 1 had been less than the injectivity radius of gamma mod x, then this list would either consist of 0 or 1 elements. Okay, these aren't enormously large lists, but maybe if you don't know how to compute the injectivity radius in advance, you want to give yourself this kind of flexibility. Okay, so say we have 3 points, x, y, and z. So we have 2 lists. Let me call them gamma 1 up to gamma n, and let me call them delta 1 up to delta m of, so these are subsets of our group gamma that move the element x close to y. If the balls of radius 1 centered at these 3 points have a common intersection point in the quotient, then in particular, there has to be one of these gammas that moves y close to x. This can't be an empty list. Okay, and similarly for z. So what you could do is you could go through sort of all n of these gammas and all m of these deltas, and then sort of translate the ball of radius 1 centered at y by that element gamma and that element delta, and then test whether those 3 balls in the symmetric space have a common intersection point. And you can convince yourself quite easily that these balls in the quotient have a common intersection point if and only if sort of among these n times m different possibilities of sort of triples of balls intersecting in the symmetric space, one of those triples has to have a common intersection point. And if none of them has a common intersection point, then the 3 balls don't intersect in the quotient. So step 1 was reduction to intersections in X. Okay, so we're back to this kind of tricky problem, or this problem I claimed was tricky even in the Euclidean plane. So say you have 3 balls in the Euclidean plane, or 3 balls in more importantly for us, in maybe a negatively curved symmetric space. So how do you determine whether 3 balls have a common intersection point? I keep saying 3, but this sort of, you're interested in this question for all values of 3. Okay. Okay, so the next step is you can reformulate the problem about whether 3 balls intersect as a problem as the solution to an optimization problem. So what does it mean for, so say you have so I called the points x, y, and z before, so I guess I'm stuck. So x, y, and z. So say you have a point P. So P lies in the intersection of the ball of radius 1 centered at x, y, and z. Exactly when, this is just the definition, the distance from P to x, the distance from P to y, and the distance from P to z is less than or equal to 1. Or in other words, when you, it implies that if you take this function, so distance from P to x, distance from P to y, and distance from P to z, take the maximum of these 3. So this is some function of the point P. For some reason, I'm going to replace these distances by distances squared. Okay? So the balls have a common intersection point. If and only if there is a point P for which the value of this function is less than or equal to 1, right? So they have a common intersection point if and only if the minimum value over all p of the function f of p is less than or equal to 1, right? But what can you say about this function f of p? So, but f of p is the maximum of 3 convex functions of p. So what does convex mean in this context? So there's a very nice notion of geodesic in the symmetric space X, and a function is convex if it's convex as a real valued function when you restrict it to every geodesic. Okay, and it turns out that the square of the Riemannian distance function because X has non-positive curvature, you can say that this function is convex. In fact, it's strictly convex, and it's a nice smooth function for which, if you restrict it to any geodesic, its second derivative is always greater than or equal to 2. And that value of 2 is the value you would get if this distance were just the Euclidean distance along a line in the Euclidean plane, and all of these spaces X somehow being more negatively curved than the Euclidean plane implies that this function is even more convex. It has even larger second derivative than if you imagine that we were in some kind of Euclidean situation. Okay, so this is for a totally formal reason, the maximum of any collection of convex functions is again a convex function. So f of p is a convex function on the symmetric space X, and you can phrase the problem of whether these three balls intersect. You can phrase it as a problem of determining whether the minimum value of this convex function f of p is less than or equal to some number. Okay? So I guess it depends who you ask. I'm not an expert in optimization, but I think that there are some people at the IAS who would say that if you've reduced a problem to some question of finding the optimal value of a convex function, you sort of solved the problem. It's that there are efficient, good algorithms to do this, and in particular, you could do some kind of when you have a nice convex function, it turns out that gradient descent always works. So you could do some kind of gradient descent method, and you could eventually converge to the minimum value of the function. So the hard thing to do, like I guess I erased the picture of the three balls without a common intersection point from before. But the hard thing to do is so if three balls do have a common intersection point, you can usually find it pretty easily. Maybe these balls have quite a thick intersection, and you try to run an algorithm to minimize this function, and you reach a point when you have found a point which is good enough, and if you have a point, it's really easy to test whether its distance is at most 1 from these points x, y, and z, right? That's not hard. The hard thing to do is, if you're in a situation like this, how do you certify that three things don't have a common intersection point? So that's a harder problem. That's a harder problem to solve. So the problem with the problem computing with these nerves is that it's so as we saw in the example from sort of a much earlier slide, it can be very time consuming to compute this. So, this so-called, this optimization problem, which presumably can be solved like extremely efficiently in a theoretical sense. In practice, like I've had something running since early this afternoon, and it's still not done. Granted, we had to run this optimization problem about 10,000 times in that example, but I mean that's just the nature of the game. That's how many triples of balls sort of have a configuration that look at least as good as this, meaning like you sort of have like for every pair of them they have a common intersection point. There happen to be about 10,000 or so of those in the particular small example that that I mentioned at the beginning of the talk. So yeah, so you're kind of forced, if you are going to compute the if the way you're going to compute the topology of your manifold gamma mod x is using a check complex, you're kind of stuck solving this optimization problem thousands and thousands of times. You need something which is, if you want to use this method, you need something extremely fast. Another thing which is a little bit thorny about the nerve, and the second point I think will make more sense in a few seconds, but it's very hard, the numbers of simplices, even in small dimensional examples. We're talking about computing the topology of a three-dimensional manifold, right? But even in that somewhat small seeming example, these check complexes that we're building have thousands and thousands of different simplices. And so at a certain point, it can become very difficult to even store, like say you need to determine when a bunch of five tuples of balls have a common intersection point. There are just lots of different five tuples that do have an intersection point, and they don't follow some obvious pattern that makes it like really easy for which it would be easy to sort of store the answer on a computer. So that becomes a problem at a certain point as well. Okay, but when Aurel and I were playing around with nerves, we noticed something.
How many you looked at 3, 4. Did you just go on until you stopped finding intersections?
Yeah. So something you can say. It's a theorem of yeah. Good question. Let me write something on the other board. So I'll just state this in R2, but it works in very generally. So if you have, suppose you have a collection B1, B2, Bn. I'll just say it for balls. So of balls, and I'll just say it in R2. And you want to know whether these n balls have a common intersection point. So this intersection is non-empty if and only if when you take any three of them, their intersection is non-empty. So the 3 is dimension plus 1. So it would be, so as soon as you've computed whether, so if your symmetric space has dimension d, as soon as you've looked at d plus 1 tuples of different balls, that's enough to, so once you know that, you know the world. Yeah. So this is a theorem due to, I'm not sure if it's pronounced Helle or Healy, but it's a theorem of Healy. Okay. Okay, so when we were playing around with these nerves, there was something we noticed. So say you look at so I'm going to draw a bunch of points on our manifold, and so this represents our subset M. And you could look, so something you could do, which is much more naive than computing a full check complex. You can, I mean, if you have three balls that have, so I know I've been dwelling on the difference between this and whether the three balls have a common intersection point, but there's still somehow a lot in common between how this looks and how three balls that have a common intersection point look. So what if you do something naive and you look at, so two balls of radius 1 intersect if and only if the distance between them is less than or equal to 2, right? So something you could do is you could look at, we didn't know the name for this at first, but I'm going to call it RIPS of gamma mod x of radius 2, corresponding to looking at sort of coverings of your manifold by balls of radius 1. So look at this. This is a simplicial complex for which, with simplices, points f0 up to f, so these will be k simplices, f0 up to fk plus 1, subsets of our grid f, for which the diameter of this set of points is less than or equal to 2. So if you have 2 points, saying that the diameter of that set of 2 points is less than or equal to 2, just says that the distance between those 2 points is less than or equal to 2, which means that the balls of radius 1 centered at those points have a common intersection point. So the one skeleton of the RIPS of radius 2r, it's exactly the same thing as the one skeleton of the check complex for the finite set of points in gamma mod x with radius r. Okay, they are identical to each other. So another way of saying this, sort of the diameter is less than or equal to 2, it's just saying that all pairwise distances between sort of pairs of points here, all pairwise distances are less than or equal to 2. Or another way of saying that is just that every fi and fj, they must be adjacent in the one skeleton. They must have they must be connected by a common edge in this one skeleton. So this is doing something naive. It's sort of you do the hard work of computing the one skeleton of the check complex, and then every time you see a triangle, you fill it in. Every time you see sort of all of the edges of a tetrahedron, you fill it in. Okay, so that's what the RIPS complex is doing, and so I can't state a completely satisfactory result along these lines yet, but what I will say is that empirically, it seems Say R is small enough so that balls of radius R are convex in gamma mod X. Okay, so it seems that the Rips complex of finite subsets of diameter at most 2R, so that should be comparable somehow to this check complex with radius R covering by balls of radius R. If the balls are convex, we know that this thing, by this old theorem of Čech and Borsuk, it has the homotopy type of M. These things have the same they have the same one skeleton. Maybe you believe that there's some relationship between the two. Certainly there's a natural inclusion from this to this. And I'll describe, there's also in fact a very natural map from the Rips complex to M. And so you might wonder, is this thing a homotopy equivalence? So is this something else I can say, by the way, is so not only do these things have the same one skeleton, but this complex has the correct pi1. Its pi1 is actually isomorphic to gamma as well. And the inclusion map from the Čech complex to the Rips complex is compatible with the isomorphism with gamma. So the question is, is this thing a homotopy equivalent? It's a little hard for a small, I guess a small radius Rip complex to actually compute the full homotopy type. But there are certain ways in which the topology of a manifold like M, they really jump out at you. For example, M is a compact manifold. It satisfies Poincare duality, right? Or M, because it's the example manifold we were looking at, it's orientable, so it has a fundamental class in degree equal to its dimension. The homology vanishes in degree that's larger than the dimension of the manifold. Right? So there are all these things that are incredibly special about the topology of a manifold M, and playing around. So in every single example that we have looked at so far, those same properties are satisfied by the Rips complex. Namely, we computed in lots of different examples the homology of the chain complex that arises from the fact that this is a simplicial complex, and when you compute its homology, it seems to always satisfy Poincare duality. It always has a fundamental class, which I think is very suggestive. But unfortunately, we don't know how to prove that these two things are always the same yet.
Sorry, so the empirical result is the vertical one, but the diagonal one is not.
I'm sorry. So if the Čech complex didn't exist, you could still ask, is this a homotopy equivalence? And what I'm saying is that there is. So if you compute, at least if you compute for example, the homology groups of this Rips complex, it always appears to satisfy Poincare duality. I guess that's really the empirical fact I'm claiming.
Have you been computing things that are bigger than 3 manifolds?
I think we've done so far maybe like one. We've done a couple 4 manifold examples. It gets hard.
Yes, in those cases, I mean, if you have Poincare duality, then you basically have shown that it is.
Yes, but so I'm not saying that we this really is empirical. I'm not saying that we systematically. I'm not saying we've proven a theorem yet that says that as long as R is a radius for which balls are convex, then there's a natural map that I.
I mean,
I think you'd be very close if you could actually prove Poincare duality in those sort of in a three-dimensional example that you'd be done. I mean, you wouldn't, because of what's known about sort of how the pi1 of M and the pi1 of the Rips complex relate to each other. But like you said, I mean, as soon as you went to a four-dimensional example, Poincare duality alone wouldn't be enough. But another thing to say is, so while the nerve is, so I said computing its higher simplices, it's time consuming and it's difficult to store. Now I can explain sort of in contrast to the Rips complex what I meant by difficult to store. The Rips complex, sort of the condition defining it, implies that the one skeleton completely determines sort of all of the higher skeleta, right? So maybe this is sort of the number of edges in this complex is going to be sort of proportional maybe to the volume of M, and sort of volume of M many bits is going to be enough, sort of that's enough space to store sort of what the Rips complex is. Whereas the check, as soon as you go to dimension D, you're looking at numbers that are more like sort of volume to the D. So it's like a lot, so it takes like a lot, much more space to store the check complexes than it does to store Rips complexes of compatible radii. So this is just one example of computing sort of some of the, I'm sorry?
Why did Rips consider?
So Rips was looking, so the reason Rips considered Rips complexes is he was interested, I think, in defining defining a homology theory that sort of that would respect two metric spaces being close to each other in an appropriate sense. So, for example, if I look at a very fine mesh inside of a manifold, as a topological space, it looks kind of silly, right? It's just a disjoint union of points. On the other hand, there's something about it that looks incredibly much like M. And if you look at the Rips complex of a very fine mesh, then it's going to have the same topology as M. So basically, I think it's to have a homology theory that's sort of defined on metric spaces that respected when, that sort of output the same answer when the metric spaces were close in an appropriate sense. And you can make that rigorous, but yeah. So this is an example of sort of, I guess I'm being inconsistent. I'm using Rips 2R versus check R here, but the 0.65 you see on this slide is meant to be compatible with the 0.65 that I used earlier for the check complexes. So the computation of the one skeleton of the Rips complex is the same as the computation of the one skeleton of the check complex, so that's why the computation times are the same. So the one skeleton totally determines all the higher skeleta. That's an extremely nice feature. And we actually had, so it didn't even take running sort of like, it took, at this point in the computation, once we've computed the one skeleton of the nerve, we're done. It's basically trivial from that point to determine it, just because anytime there is a triangle, you fill it in. So it's very easy to count the number of 2 simplices and 3 simplices and so on, and here are the numbers. And the homology of the Rips complex, it gives the right answer. Because Rips happens to be correct on pi1, I guess we knew that this was going to happen. But we did an honest computation of this. We took the simplicial complex given by the Rips complex, and we computed its homology, which we did mod p for some small p, because it turns out that computing rationally with enormous matrices is much more complicated than computing mod p. Maybe that's no surprise, but But anyway, the sort of the mod 2, mod 3 Betti numbers, they look correct. They're consistent with the abelianization of the fundamental group. And then for primes that have nothing to do with the 2s and the 3s that occur here, you get the right answer. You get sort of 1 in dimension 0 and 3 and 0 in other dimensions. Yeah, so empirically this is a success, and I pose as a challenge: is it true that you can prove that this Rips complex is actually homotopy equivalent to M? And since I have almost no time left, let me just end with the statement of one thing you can prove in this direction. Unfortunately, in practice, it's not good enough, but it might sort of make you somewhat optimistic. So let me actually just state this for the. It won't be a finite subset anymore, but we're going to be looking at kind of a mesh in the symmetric space itself. Okay, and say so. So suppose F is R dense, meaning that every point in X has a point of F that is R close to it. Okay? So suppose F is like quite a dense subset of your symmetric space, then so if R prime, I think if it's greater than something like 17 times R, then, so if the Rips complex of F, whoops, so I'll say the Rips complex of radius R prime of this finite, or not finite subset of this kind of this grid inside of X. So if this has the same topology as X, it should be contractible, right? And this is true. And this is contractible. And to match up with sort of the challenge problem that I posed, that would somehow amount to improving this 17 to a 2. So in just 5 seconds, let me say that I guess the. I'm sorry?
Is it important whether it's
Yeah, for practically it is. So the issue is. So what we'd like to do is to compute the sort of the homology, say, of a Rips complex of a set of a grid of points on our manifold that is R dense for some R. And then what we're saying is we have to make something, I'm going to mess up the numbers in my head. It's either 17 times more dense or 8.5 times more dense than that set of points. But what does that do to the total number of points? Like if you think of the number of points in a ball, if you have like kind of a grid in a ball, and then you increase the density of that grid by a factor of 17, you're roughly going to increase the number of points in a ball to like 7 by a factor of 17 to the power of the dimension. Now the dimension is fixed. We're working with a 3-dimensional manifold. On the other hand, for a computation that's already like quite complex, it's kind of hard for it to terminate. It doesn't help if you sort of increase the running time by a factor of 17 cubed. So that's the significance of the 17. It really would be important to make this specific result practical, to make that number 17 smaller. Theoretically, I'm just as happy with 17 as with 2. And in the paper that we write about this, proving sort of the first slide that I had, it's going to take a while to go to is there a go to the beginning button? Maybe not. Anyway, it'll take me a while to click back to the beginning, but all I was there are some bounds for that we give for the total number of simplices in the simplicial complex that we build, namely some kind of Rips complex. Almost there. And there are some big O constants, and those constants are going to be exponential in the dimension, and sort of the difference between a 17 and a 2 is going to be sort of like multiplying the exponent in an exponential by 8.5. But practically, that's kind of devastating. Theoretically, no big deal, but practically, it's an issue. But I'll end here.